Okay, welcome back. We're going to look at a comparison of series. Basically, you'll be given a series that kind of looks familiar, something like, consider something like 1 over square root of n plus 2, right? This kind of looks like, the p series, 1 all over the square root of n. Of course, that thing is divergent because it's a p series. And the p-value is equal to 1/2, which is less than or equal to 1. Okay, so we hope that maybe if this thing is divergent, that'll tell us that the other guy is divergent. Does that kind of concept fly? It'll turn out it kind of does, but there'll be some criteria you need to make sure hold before you go ahead and do that. And it'll become like a three-step process. So let's kind of like take a look at the theorem. Okay, so there's two tests here. There'll be the comparison test and then the limit test. We want to start with the comparison test. So the comparison test, we'll look at theorem. I think it's 9.12. Where the heck is it? Jeez, I just love it when the thing starts scrolling on its own. Yeah, theorem 9.12. And basically you have two series that you're dealing with. The terms of the series are all positive. And then you could say first, if the series with the bigger terms converges, it'll force the series with the smaller terms to converge. Then if the series with the smaller terms diverges, then the series with the bigger terms will diverge as well. Okay. You have to be a little careful because there's things that this guy does not say. It does not say that if the series with the smaller terms converges, that the series with the bigger terms converges as well. It says nothing in that case, right? Likewise, it says nothing when the series with the bigger terms diverges. The series with the smaller terms, in that case, may either diverge or converge. You don't know. So you have to be very careful with this test. It's not just a blanket type thing. We could take a look at the proof. I'll just prove the first statement and then use logic to conclude the second statement. Okay, so the proof of 1. Basically, you've assumed in 1 that the series B sub n converges. So we suppose the series B sub n converges, and of course 0 is less than a sub n is less than b sub n for all n. Okay. Then consider the sequence of partial sums for the series with the smaller terms. So consider S sub n for the sequence of partial sums for the series n equals 1 to infinity of a sub n. Right. So S sub n, the nth term of the series. So let me rewrite S sub n as a sequence. But anyways, S sub n literally equals a sub 1 plus a sub 2 plus dot 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 all the way up to a sub n. Then because of our inequality, we can say the following. We could say S sub 1, which is equal to a sub 1, will be less than or equal to b sub 1, which of course in turn then is less than or equal to the infinite sum of the b sub n's. Because b sub n converges, we know that this series n equals 1 to infinity of b sub n will equal to some number, we'll just say L. Okay, then S sub 2, of course, will be A sub 1 plus A sub 2, which will be less than or equal to B sub 1 plus B sub 2, which again will be less than or equal to the total sum, the infinite sum from n equals 1 to infinity of B sub n, which equals L. And you can repeat that game until you're getting S sub n, and then you'll note that no matter how you slice S sub n, it's going to be bounded above, and well, the sequence will be bounded above, and it'll be increasing because all the terms are positive. So you'll have that again, this monotonic increasing issue, and so it'll be convergent. So note S sub n equals the sum from, let's say, n equals 1 to, well, I guess we have to use different limits because we're using n on the outside. So we'll say I equals 1 to n of a sub I. That'll be less than or equal to the infinite sum n equals 1 to infinity of b sub n, which will be equal to L. And for all n, really. So at the end of the day, given the a sub n's are greater than 0, we conclude the sequence of partial sums S sub n, the sequence S sub n, is increasing and bounded above. And thus convergent. Okay. The second part then just follows from the contrapositive of the part 1, right? So proof of 2. So the first one says if B sub n converges and A sub n converges. So if the series B sub n converges, the series A sub n converges. Or maybe we should write then, right? If then. So the contrapositive means you kind of negate each part and then reverse the direction of the implication. So taking the contrapositive, which is logically equivalent, we have that if the series A sub n diverges, then the series B sub n diverges as well. Okay, so in proofs, you're usually kind of working not just with your knowledge of mathematics and kind of the common sense issues that you've grown up with. You're also kind of tacking on now a lot of logic. So you may have seen logic applied in geometry and stuff like that, but you can use a lot of like the logic that you would take in a logic class at college here in this context to generate theorems, so long as you use accepted logical sequences of thought, right? So anyways, there's that. Let's look at how these problems go and how they are kind of applied here. Okay, so I'll just call this part A, the application of the theorem. It should always be in 3 steps. So first, you're going to make a comparison of the terms of the series. Secondly, then you're going to state the convergence or divergence of the series that you're comparing it to. So basically, you'll be given like the series here, and then you'll have to generate this series. It's a series that you know. Okay, so it'll have to be something you could prove is divergent or convergent using one of the tests that we've developed, or just by looking at it. Is it geometric? Is it a p-series? That kind of stuff. Okay. So secondly, then you have to state the divergence or convergence of the series you're comparing it to. Series you are comparing. And then thirdly, you'll make your conclusion. Okay. I think the hard part is to compare the terms, because this is not something that they generally teach you how to do like in an algebra class, and you could kind of get a taste for it in example 1, example 2 in the book. Let's look at example 1. Okay, so they're giving us a series 1 all over 2 plus 3 to the n. And first I would kind of make the comparison. So there's kind of two directions you could go with a comparison. You could go 1 all over 2 plus 3 to the n. You can make the denominator bigger or make it smaller, depending on what you're trying to get, right? So if you're trying to show that the series is convergent, you want to make a series that has terms that are bigger. Okay, so you're going to effectively make the denominator smaller. To make the denominator smaller, you kind of just chop off part of the denominator. So I'll just end with 1 over 3 to the n. Okay, so this is a good thing because I can acknowledge what that formula. It's geometric. It's convergent because the r value is less than 1, right? So that's one direction. So if you want to show basically so what have we done? We've made the denominator smaller, so that second expression will be bigger, and so we want this thing to converge. Okay, so if you want to show convergence, you need this type of inequality. All right. If you want to show divergence, the trick to pulling that off is to kind of 1 all over 2 plus 3 to the n. We want to make the denominator then bigger, right? So if we need this other directional inequality and we know the series on the other side is divergent, we want to make it this way. So if you want to show divergence, the trick will be to kind of replace the term that you would normally chunk in the trash with another term 3 to the n. So 3 to the n will be bigger than 2 for n greater than 1, right? Because if n is 1, it would be 3. If n is 2, it would be 9. So you just rewrite this as 3 to the n plus 3 to the n. That will increase the denominator, therefore decrease the overall expression. And not only that, it's just a constant multiple of the terms of a geometric series. So you may have forgotten, but if this series a sub n diverges or converges, or maybe we can write it in a more quicker way, the series a sub n and the series of a constant times a sub n both diverge or both converge. I'll just say both have the same behavior. Okay. So if you are doing the second comparison, this series right here will, in this case, it'll be a constant multiple of a geometric series. The geometric series given, 1 over 3 to the n, is convergent, so therefore a multiple of that geometric series will also be convergent. Okay, so this thing up over here is convergent. Unfortunately, in this case, it won't help, right? Because you have the series below it converging. That tells you nothing about the series above it. Okay, so we are going to use this first inequality. Secondly, in the kind of program that I want you to show on the test, you need to make a statement about the series you're comparing. Right? This 1 over 3 to the n is basically just a geometric series with r value 1/3. So you have three things to say. What kind of series is it? It's geometric. What's its particular criteria? The r value equals 1/3, which is and we talk about absolute values when we talk about geometric, so that's less than 1. And then your conclusion is that it's convergent because of that criteria. Okay, so where we have a series on top that is convergent, therefore the series below it is also convergent. So the original series converges. Okay. Let's look at the second example in the book then. And I think this will have to go in the other direction, right? Because I have the feeling that this thing's going to be divergent, so I want to compare it to a series that has terms that are less than the terms of this series. So let's look at example 2 then, and go with that, right? So 1 all over 2 plus square root of n. A series of 1 all over 2 plus square root of n. I kind of disregarded kind of where the series begins. It's as long as it holds eventually, it's going to be okay. But if you want to be more technical, more careful, you're going to become a mathematician or something, you need to note these n values. Okay, so this inequality will be true for n greater than or equal to 1. Okay, let's go to the second guy then. The terms of the limit of the series is going from n equals 1 to infinity again. First, we'll make our comparison. 1 all over 2 plus square root of n. Because I have a feeling this is going to be divergent, I need something less than that, so I need to increase its denominator. So again, you play this game, square root of n plus square root of n. So I note sort of over here to the side, the square root of n will be greater than 2 for n greater than 4. Right? Because if n is greater than 4, you can kind of raise both sides to that 1/2 power, and you get the square root of n is greater than 2. So there are, a lot of axioms with regards to inequalities that you may not be familiar with because they don't really study them that much in math. But if you get it more into proving math statements, so if you're like in the math Olympics or something, you really need to know the axioms of inequalities. And one of them is you could raise both sides of an inequality to exponent powers so long as the two sides of the inequality are both positive. And in this case, that's what I did. I just raised both sides to the 1/2 power. So if I assume n is greater than or equal to 4, I can square root both sides and get square root n is greater than 2. Okay, when n is greater than 4. So as long as it holds eventually, you can make conclusions about the divergence of convergence. If you're forgotten, there is a fact that says, and I think I gave it to you in 9.1, if the series, or let's write it in kind of the shorthand way, basically the series n equals 1 to infinity of a sub n and the series from n equals m to infinity of a sub n both have the same behavior. In other words, if you can prove that this guy is converging, it'll automatically show that this guy is converging. Okay. So long story short, as long as you could push it out to somewhere where the inequality always holds, you're going to be safe. It'll show the desired statement. So in this case, what have we done? We've increased the denominator, therefore decreased the expression. 1 all over 2 plus square root of n will be greater than this other formula for the terms of the series. That thing is 1 all over 2 times square root n. So then we talk about that particular series, the series of 1 all over 2 square root n, right? Because square root of n plus square root of n is 2 square root n's. What the heck is this thing? This is a p series, but it's a constant multiple of a p series, right? So it's 1/2 times 1 all over n to the 1/2. So I'm going to note that this is divergent. It's constant multiple of a p series. I'm sorry you couldn't see that. P series. And the p-value here is 1/2, which is less than 1, which, that's the criteria for being divergent. Okay, so once we have established that, the smaller the series with the smaller terms is divergent, that forces the series with the bigger terms to also be divergent. So the conclusion is that both diverge. Okay, so yeah, it's kind of the big and the small for this. The they have this last statement here again reminding you that you have to play this game. If the larger series is divergent, it tells you nothing about the quote-unquote smaller series. So speaking informally now, but I mean technically you're just talking about the terms of the series. It's not necessarily that one series is, you know, for a fact is bigger than the other. So if the terms of the series, the terms of the series, if the series with the bigger terms is divergent, it says nothing about the series with the smaller terms. But if the series with the bigger terms is convergent, then the series with the smaller terms will be convergent. So just be careful. You can't just blindly apply this theorem to anything you want, and that's why this theorem is kind of, in my opinion, more difficult than the limit comparison test, which is what we're looking at next. Okay, so section 2 then, we have the limit comparison test. And the limit comparison test hinges on theorem 9.13. Again, I want you to kind of do it in 3 steps. You'll first, in this case, you have to find a series to compare it to, then you take the limit, and then you make a conclusion. So again, you'll have terms of the series which are all positive. So if a sub n is greater than 0 and b sub n is greater than 0, and you take the limit of the ratio, and it could be a sub n over b sub n or b sub n over a sub n, it won't matter, but in the book they're going to go a sub n over b sub n. If that limit as n goes to infinity equals L, and L is greater than 0 and finite, then the two series will have the same behavior. The series a sub n and the series b sub n have the same behavior. Okay. A lot of people think that just automatically, if the limit is equal to L, they both converge. And that is a huge reason why we try to force these proofs down your throat. It's actually, when I was a student, they made us memorize all these proofs. Okay. I'm not going to do that to you, but I'm just going to say, if I see you applying these theorems or asking me, hey, I got the limit to equal 5. How come the thing isn't convergent? I'll say, read the proof. Okay, if you read the proof, you'll understand why the criteria are the way they are, and you'll have a bigger understanding of the picture. Okay, a more general understanding of how these guys behave. So, anyways, let's really quickly just take a look at the proof. My proof is a little bit different than what the book does. So let me. I will suppose the same elements. So suppose the terms of the first series are positive and the terms of the second series are positive, and you have this limit of holding. The limit as n goes to infinity of a sub n over b sub n equals some number L, which is greater than 0 and finite. Okay. So suppose a sub n is greater than 0, b sub n is greater than 0, whoops, and the limit is greater than 0 and the limit is finite. So maybe I should also say that. So sorry about my English here, it's just atrocious. And the limit is finite. Okay, so what we're going to be able to do, because of the strict definition of limits, we know that for some big N value greater than 0, we can kind of wedge a sub n over b sub n in between two positive values. Okay, so let's call the bigger one big M. I'll maybe make it like a big cursive M, and the little one little m. Okay, and these will both be greater than 0 for eventually, some little n greater than big N. Okay, so if you don't remember kind of how the limit definition works, basically, as you go out further and further, and we know the limit of a sub n over b sub n is equal to some number L, which is positive and finite. So let's say this is L. As you go further and further, so as you get past this big N, the terms of the sequence, no matter what they were previously doing, will kind of have to get within some epsilon of L, right? So you'll be able to then kind of make this inequality statement if you just let this lower kind of part of the parentheses be little m, and the upper part of this parentheses around L be big M. Okay, so as long as you get far enough out, all of the terms of the sequence will be within whatever epsilon you want, but in this case we'll just say big M and little m. Okay, so all the terms will end up in here, whatever the heck they're doing. Okay, let's make this, it just looks like a mess. So big M is up there, little m is down there from the strict definition. So for some n greater than 0, we can make this an inequality. And then we can multiply through by b sub n. You know, why not? So multiplying by little b sub n, we get that 0 is less than little m times b sub n, less than a sub n, less than big M times b sub n. And what you have is kind of the beginnings of the direct comparison test, right? So so we have then if the series b sub n diverges, then the series m times b sub n diverges because it's just a constant multiple of a divergent series, which will also be divergent. Thus, the series with the terms that are bigger than the terms of the series of m b sub n, that thing will be forced to diverge by direct comparison. Thus, the series a sub n diverges by direct comparison. Then likewise, if the series b sub n converges, well, we have that big M times b sub n being greater than a sub n, so the convergence of the series of big M b sub n, which is just a constant multiple of a convergent series, will also converge. Then that converges, and so the series a sub n, again, we'll use the direct comparison test and say that converges. So, and the series a sub n converges by direct comparison. Okay, so that's why we have the conclusions that we do. It's not just that if you have a limit that converges, well, then they both converge, right? No, it's the convergent of this ratio allows us to kind of build an inequality that allows us to take advantage of the direct comparison test, and then we make our conclusions about the behavior. So let's look at, I guess, example 4. And we want to use limit comparison test on this thing, square root of n all over n squared plus 1 from n equals 1 to infinity. I'm gonna, so that my first, so the way you want to do that first is kind of produce the series you're going to compare it to. And generally what I'll do is just chop parts off. So I'll just look at the series with that stuff in blue that I just circled. So I'll compare with the series square root of n all over n squared, okay, which of course is just n to the 1/2 all over n squared, which of course is just a series of 1 all over n to the 3/2. You know, 4/2 minus 1/2 is 3/2. And then that thing, what is it? Well, first off, it's a p-series. Looking at the value of the p-value, it's p equals 3/2, which is greater than 1, therefore it's convergent. Okay, so you need to show those three factoids. And then secondly, you can go to the limit, and then thirdly, I would expect you to show me or tell me the conclusions. So the second case, you're doing the limit of the ratio of the terms of those two series. Okay, you can put either one on top, it don't matter. I'll put the first one on top. So 1 all over n to the 3/2 divided by the square root of n all over n squared plus 1. Okay, as n goes to infinity always. So take the reciprocals, you get 1 all over n to the 3/2 times n squared plus 1 all over n to the 1/2, basically. That will equal limit as n goes to infinity of n squared plus 1 all over n to the 3/2 plus 1/2, which is 4/2, which is 2 n squared. And then if you remember kind of our shortcut for evaluating these ratios of polynomials, you could just look at the high degree terms, and basically the limit of n squared over n squared is just the limit of 1, which will equal 1, which is greater than 0 and finite. Okay, so what have we done here? We've gotten the criteria that we need to hold, and then we could say both series have the same behavior. In this case, they both converge because we compared it to a convergent series. Okay, so hence both converge. Okay, so again, note, just because you get a limit out of it, it does not automatically imply convergence. Let's look at this example 5. And we have the series from n equals 1 to infinity of n 2 to the n all over 4n cubed plus 1. So again, figure out what you're comparing to. So I'm going to just look at that part, chop off the plus 1 part. So I'm going to compare with the series n times 2 to the n all over 4n cubed, and then you could simplify that into 2 to the n all over 4n squared. You could get rid of, the book gets rid of that constant 4, which is perfectly legal because it's not going to affect the behavior of the series, right? So you just look at 2 to the n over 4n squared if you want. It's not going to matter. Anyways, you can do the nth term test on this. So note the nth term test to prove whether it's convergent or divergent. The nth term test proves divergence. Okay, so as long as the limit of the terms is not equal to 0, it'll diverge. So note the nth term test for divergence. You take the limit of the terms of the series as n goes to infinity. This is an infinity over infinity, so you can do L'Hopital's. You get the limit as n goes to infinity of 2 to the n times ln of 2 all over 8n. Then you could do L'Hopital's again because this is also infinity over infinity, so you get the limit as n goes to infinity of 2 to the n times ln of 2 times ln of 2, so ln of 2 squared all over 8. And then of course this thing will just shoot off to infinity. And it doesn't go to 0, right? So the infinity is clearly not 0, hence the series diverges. Remember, if this limit does equal 0, it doesn't imply that the series converges, right? If you look at the limit of the terms of the harmonic series, which we know is divergent, the limit of that thing is equal to 0. So the nth term test for divergence there tells you nothing. Says nothing. So be careful with that test. But anyways, in this case, it doesn't go to 0, so therefore it's divergent. So hence the series diverges. So secondly, then we make this limit. So note the limit of the ratio of the terms of these series. So I have, I'll put the 2 to the n all over 4n squared in the top, and then the bottom you have the same thing, but there's a plus 1 involved. 2 to the n all over 4n squared plus 1, limit as n goes to infinity. So this will be the limit as n goes to infinity of 2 to the n all over 4n squared times 4n squared plus 1 all over 2 to the n. These guys cancel, get the limit of 4n squared plus 1 all over 4n squared. You could just look at that part. That's just the limit of 1, which of course equals 1, which of course is greater than 0 and finite. Hence, both have the same behavior. And note, the limit equaled something, but that does not mean it's convergent, right? So they both diverge. Okay, great. I still didn't do a video quiz question. Let's see if they got any more. No, they don't. Okay. Let's do a homework question then for the video quiz. Sure, we'll do number 4 here. Maybe even number 5. For number 5, the comparison, maybe it's not clear how you should compare that. Number 5, this isn't the video quiz. You have the 1 all over n factorial. You may have remember the limit of k to the n all over n factorial as n goes to infinity will always equal 0. In other words, any k value to the nth power will be less than n factorial. Okay, so when you go to make your comparison in that first kind of step I want you to do, you'll have 1 all over n factorial, and you'll think, well, hey, this probably converges because that denominator is getting so big so quickly. So you're going to try the bounded above, or bounded below, bounded above by something that's divergent, or something that's convergent, bounded above by a convergent series. So I'm going to say that this would be, I'm going to decrease the denominator, therefore increase the entire expression. So if you use some power of like 2, you could say 2 to the n, that thing will, the denominator now is bigger, right? So the denominator now is smaller, so the overall expression will be bigger. So it'll be that direction of inequality, and it won't hold for n. I don't think it will hold from n equals 0 to infinity. It holds for n maybe greater than something. So if you look at the first couple terms, it's 1 over 0 factorial is 1, and then on the other side it's 1 over 2 to the 0, which is 1. So it doesn't hold for n greater than 0, which just seems to me as kind of an issue with their. So it's less than, we'll say 1 all over 2 to the n. Let's make sure that works. Obviously on my test you can't just say it's convergent or divergent. You have to go through this 3-step process. But anyways, we'll say for safety issues, it's 1 all over, I mean even n equals 1 won't work, right? Because you get 1/2 and then 1/2. At 3 you get 1 all over 6 and then 1 all over 8. So that then still doesn't work. So at 4 you get 1 all over 4 factorial, so 12, and then 1 all over 2 times 4, 8, 16. So finally, is that working? I'd rather have 1/12 of a piece of pie than 1/16. Well, gee whiz, 0, 1, 2, oh, this is 4, sorry. And then this would be 8. So now it's working. Yeah, so for n greater than 3, it'll start working apparently. You would have to prove that if you're like in a proof class. For me, I don't need you to do that. I don't even really need you to say for what n value it works. But then you have the series of 1 all over 2 raised to the nth power. So what is that? That's geometric. R is equal to 1/2. The absolute value of R is equal to 1/2, which is less than 1. So therefore it's convergent. And hence our conclusion is they both converge. Okay. Let's make number 4 then our video quiz. Let me mark it down. This is the 4th video quiz, and I know I forgot to give you the video quiz in 9.3, but it was problem 7 in WebAssign. I put it in the comments there. Anyways, 9.4, the fourth video quiz, and this is the fourth question in video quiz set number 6. So it's question 4, which also happens to be the fourth question in the video quiz set. Okay, so 9.4, number 4, we have a series of ln of n all over n plus 4. Okay, so I want to compare this thing to something. Oops. Okay, hold on one second. Okay, so we want to compare this thing, and it's a little bit different than kind of just getting rid of the 4 in the denominator, or maybe adding in another n instead of the 4. First off, let's think about what this thing is, right? Is it going to converge or diverge? And I think because that ln grows so slowly, the main portion, the main idea is going to be the n plus 4. That's going to kind of take over, I think. So what I would say is that it's going to be divergent. It's going to be like 1 over n. It's going to be like the harmonic series. But in order to pull that off, you need your inequality on the right to be less than. I mean, you need the inequality to be less than, right? You need whatever the heck this thing is to be so I need this inequality. I need this thing on the right to diverge. That will force the thing on the left to diverge. Sorry if I sort of bumbled my English there. Yeah, so you need this type of inequality. And so in order to pull this off, I need to increase the denominator. So I'm going to, instead of going n plus 4, I'm going to go n plus n. And in the numerator, to decrease it, all you have to do is put a constant up there. You know, ln of n will be greater than 1 for n greater than, I guess, e, or 3. Or so we would say n greater than 4. This will work. Okay. So anyways, I think the series is kind of given that way as well. Is it? Oh, they went from 2. But you, like I said, you could always kind of push it out, and if this thing diverges, it'll still work. Anyways, what is that thing? It's 1 all over 2 to the 2 times n. There's 2 n's in the denominator. So what is that? The series 1 all over 2 times n. This is a constant multiple of a harmonic series, a p series, right? For harmonic series, you don't have to say much. You should say it's divergent. Something like the harmonic series diverges. You don't have to say it's a p series with p equals 1 and therefore divergent. It's just automatically the harmonic series diverges. So therefore, this series diverges. Okay, so you have the series with the smaller terms diverging. That forces the series with the bigger terms from the first step, the inequality, to diverge. Okay, so both diverge, and that should do it, right? So ln of n all over n plus 4 will be greater than 1 all over 2n, and then they will both diverge. And it's happy. Okay, you know, on my test, you have to have the 3 steps, the correct type of inequality. So again, remember, if the series with the bigger terms is divergent, that tells you nothing. You need the series with the bigger terms to be convergent. That'll force the series with the smaller terms to converge. If the series with the smaller terms is divergent, it'll force the series with the bigger terms to diverge. If the series with the smaller terms is convergent, it tells you nothing about the series with the bigger terms. If the series with the bigger terms is divergent, it tells you nothing about the series with the smaller terms. Okay, so I know it's annoying, but that's the way these are. And okay, so anyways, thank you for watching as usual, and I'll see you next time.